Hello everyone, my name is Rabia Askar. I'm a research engineer at INRIA and I'm going to present my paper titled Vehicle Localization based on Visual Lane Marking and Topological Map Matching. Accurate and reliable localization is crucial to autonomous vehicle navigation and driver assistance systems. In urban scenarios, offline digital maps are readily available and are commonly fused with onboard vehicle sensors. An accurate map helps integrate acquired sensor data and also provides information that is outside of sensors' reach, thus providing complementary benefits. Localization approach described here is based on extended Kalman filtering. The multi-sensor EKF uses GPS and dead reckoning, as well as two distinct map matching algorithms. The state vector xk consists of vehicle's pose, twist, and linear acceleration in three-dimensional space. Geographical Information System (GIS) represents offline map database that provides layouts of the drivable lanes and central lane markings. To incorporate GPS measurements and map matching in local navigation frame, we use ENU coordinate frame. Let's first take a look into visual lane marking based map matching algorithm. Map information is translated to a 2D grid representation that we refer to as a map grid and is shown in the leftmost figure. The grid represents three spaces: road in white, central lane marking in gray, and no road in black. We extract the central lane marking and road edges to perform lane level map matching. They are illustrated by white cells in the middle figure and represent target points for the map matching algorithm. A particle filter based lane tracker is used that takes camera image and its intrinsic and extrinsic parameters as input and provides road parameters. This information, along with the EKF predicted pose of the eco vehicle, is used to project potential lane marking points on the map grid. This is illustrated by the green cells and represents source points. For each source point, corresponding lane marking target points on the map grid are selected. In 2D, Iterative Closest Point (ICP) algorithm is used to make pose correction between the two sets. EKF predicted pose is taken as the initial guess for ICP. The corrected pose is introduced as a new observation for EKF. Now moving on to the topological map matching algorithm. For TMM, lane level waypoints in the map database are defined as a topological graph comprising of nodes and directional edges. They are represented by dots and arrows in the figure. The map matching algorithm uses if-then-Gaussian rule approach to snap the vehicle's position onto the most appropriate edge. Initially, feasible edges are shortlisted around the estimated vehicle position. For the ego vehicle positions in green, only the edges in blue are considered for TMM. With availability of new vehicle pose estimate, TMM algorithm snaps onto the closest edge to the vehicle's position. For every new edge snapped, the algorithm verifies that the current snapped edge has a feasible path to the new edge. If not, TMM algorithm enters a conflict resolution mode. Figure here represents a scenario where conflict occurs at an intersection. The algorithm resolves the conflict by checking if any of the previous two edges has a feasible path to the new edge and then also to the subsequent edge. This holds true for the conflict shown here. Otherwise, if this is not the case, alternate new edge are considered. Since TMM algorithm operates by snapping onto an edge, it always provides information about vehicle's position, PTMM, strictly onto the center of the lane. However, the vehicle's actual position can be anywhere along the width of the lane. So, making a periodic TMM observation as a Gaussian distribution with mean value PTMM will be inappropriate. Therefore, we propose to only make the EKF observation when the estimated pose of the vehicle is out of the lane. An example scenario is illustrated by yellow ego vehicle here. where the estimated position is outside of the lane. TMM observation, YTMM, is represented by the black triangle in the pale yellow EVO vehicle. The TMM observation equation is defined in the ENU coordinate frame, similar to the ICP observation. Experiments were conducted on a Renault Zoe vehicle running on an average speed of 60 km per hour. The test course used was about 2.2 km long and included a speed bump and a roundabout. The update rate for visual lane level map matching algorithm was 10 Hz, while TMM observations were non-periodic. OpenStreetMap was used to define grid and the topological map. We used AppleTag visual fiducial detection algorithm at 4 fixed and known positions in the map in order to evaluate the performance of the localization algorithm. The figure illustrates the respective position of the tags and the experimental route on OpenStreetMap. Here's a video of a vehicle run on the test route. 3 sensor fusion use cases were considered to compare and characterize our approach. A localization by our proposed approach is shown in red. The one without TMM is shown in blue. And the one approach with no map matching algorithm is represented in green. The difference between the 3 approaches is most significant at curves. It is visible that our proposed approach recovers fastest when pose drifts out of the lane. As a measure of deviation in the localization results in each of these 3 approaches, we take note of the time interval during which the estimated vehicle position remains within its lane. Our approach is efficiently able to localize the vehicle within the lane for a mean of 99% of the runtime. For each tracked frame detected, lateral and longitudinal error in the position of the vehicle was determined. The lateral errors for all the tags remained within 1 meters, which conforms with the observation that the estimated vehicle position always remained within the lane in the test area close to the tags. All tags have maximum longitudinal error within 2.5 meters. Both tags A and D were recognized at a region of high vehicle speed, which contributed to higher spread of the longitudinal error. In conclusion, a new approach to the vehicle localization is presented that fuses visual lane level and topological map matching with GPS and dead reckoning. The proposed approach has been validated on real-life conditions on an equipped vehicle. Detailed analysis of the experiment's results show improved localization using the 2 aforementioned map matching algorithms. Moreover, accuracy of the localization of the vehicle was established at 4 points of interest using visual tags. Future research will study the use of RTK GPS to define a high-definition map that will further increase the accuracy and robustness of our localization approach. We also plan to integrate lane change assist to support localization in scenarios where the vehicle overtakes or changes lane. Thank you for your attention.